Last time I show you a two-way factorial design and then saying that the key is parallel. Whenever it's parallel, means there's no interactions. For factorial design, okay, on one hand, if everything is parallel, you don't have job security because everything's additive, right? Because if it's parallel, doesn't matter. You're doing doing B low, B high, A low this way, or the other way around. Doesn't matter. Parallel is parallel. Okay, so when everything's parallel, it's boring. But on the other hand, if you're gonna end up with a lot of non-parallel, okay, that's dangerous too. So usually I like to have one or two parallel, one or two interactions in your term projects or your senior design. Okay, and this could be 3-level. If it's 3-level, then you know that you still can talk about parallel or not parallel. And of course I need to rotate this until they become parallel. Okay, that's the first things we're talking about. And the second thing we're talking about is that, okay, repetitions, replica, it's daydreaming. Okay, in real life, every observation takes time, costs money. Well, even for your senior project or for any projects, okay, sooner or later you're going to encounter the same problems. Hey, who's going to collect the data? Everybody's, I have an interview, I have an intern, I have a job, so I have a date. Something is interrupting your busy schedule, and somebody will say that we don't have money to do this. So repetitions, of course, cost money. But on the other hand, what's the benefit of having replicate? Your error term will have enough degrees of freedom. But sooner or later, that's the things we're trying to figure out, is that to study the main effect, you need degrees of freedom. To study the interactions, you need degrees of freedom. To have the f-test, chi-square over chi-square, you need the error terms, you need degrees of freedom. So how to demonstrate your intelligence is not just plug and play. It's how to find a way to say, see, I have some priority. Okay, I investigate things I need to investigate first. I find a way to get things done with as few replicates as possible. Okay, that's the second take-home message, that you should kind of like getting brainwashed by me more than once by now. Okay, and of course I will show you how different tricks that we can use to do that. The second thing is this. Okay, you basically can look at the sum of this, or divided by 3, get the average, and look at this. Low is 80. Okay, and then move to low high low, and then high 90. So, well, I can just do a simple Excel here. Okay. A low, A high, B low, and B high. And rather than putting 3 value, I'm just using 1 value. I'm just using low is 3 of them. it's about 80. And A high, B low is 100. And here low high is 60. And high is 90. Okay? Now, from here to here, the jump is what? 20. From here to here, the jump is 30. From here to here, the drop is 20. From here, the drop is 10. Just by looking at the jump and the drop, do you think there are some interactions involved? Are they parallel? They're not, right? So you can plot it, right? So you can plot it. Insert here, and seeing how they drop or how they increase at different level. And of course, that's intuitions, but the intuitions can be investigated through these equations. And your homework basically said how to get this done. Rather than using the central station, subway station approach, we're using estimation of the effect and then square them and get it done. And finally, you will reach the SEM ANOVA table. So, without any review, you know that in the exam, there will be something related to 4 different ways to find the ANOVA table, right? The 4 different ways is the central stations approach, the this high, low things, and then the 2 regression approach. One is using 0, 1 dummy. The other one is using -1, +1 dummy. They're just different way to look at the same things. If you cannot reach the same conclusions, double check your answer. Okay, something is wrong because geometrically, you're looking at the world by saying, hey, here is a frame of reference, central station, a little above, a little below, okay? And here is a square dance, positive, negative. And then you're saying that, okay, let's look at it like a regression. So here is a line, some above the line, some below the line. There are lack of fit, there are pure errors. However, when I consider their jump, due to 0, 1, 0, 1, or their jump, -1, +1, you will come up with different regression estimations. Okay? Which one is 2-step jump? 0, 1 or -1, 1? -1, 1, because -1 to 0, 0 to 1 jump. Okay? Make sure that that kind of intuitions, don't memorize it. You should know that, okay? Okay, so today we're going to move to the 3 level. So rather than a square, now we have a cage. And if I have a cage, then I have low for A, low for high for A, low for B, high for B, and low for C, high for C. So low, 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 still using the parentheses 1 as my 0, 0, 0 conditions. Okay? And the 1, 1, 1, everything is positive, 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 will be the ABC conditions. And everybody, please remember, okay, how many corners we have for a cube? How many corners we have for a cube? Huh? 8, right? Yeah. Well, that's our low, low, high, high, where they're coming from, right? How many planes do we have for a cube? 6. Tears in my eyes. Okay. So if I have 6 planes, okay, but I have this many tubes, I'm basically said that I can use them to build different contrast, just like the 2x2 situations. So for the 8 of them, okay, you can consider this. This is the classroom, okay? This is exactly the 8 points, okay? So that point is my 0, 0, 0. Low, 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 low. Okay? And then that corner of the ceiling over there, that's A, B, C, everything's high, high, high. And then when you look at this, if I'm using the left wall against the right wall, is everything A is low against everything A is high. Okay? So this two wall build the effect of contrast of low A wall versus high A wall. Next, if I'm using the wall behind me, that's when everything's up B is low. Against the wall on the other side, opposite my podium, that's everything is high, high, high. So that's B low against B high. So that's B low against B high. Still, I'm studying the main effect. Finally, my floor is everything C is low, and my ceiling is everything is high. So ceiling against the floor is the main effect C. So A is A wall positive average against A wall negative. And sometimes I'm lazy. I'm just sum of the A wall, sum of the A wall, and then divided by 4 because they're balanced. Right? So divided by 4 before, divided by 4 after, same things. Next, okay, now it's become tricky. If it's this main diagonal against this main diagonal, it's what? Whenever AB effect, A and B both are 1. Against AB both are negative 1. So now this is when AB both exist against AB not exist. And then of course I can have another crossing. This time is this against this. And finally I can have another slide into and slide outward. That is my BC effect. Okay? So far so good. Finally, that's the tricky part, is this. I will have a diamond or pyramid. That pyramid is the pyramid when my base start with nada, nada, nada. Nothing, nothing, nothing. 0, 0, 0 side. And then the other one is when A, B, C are high. So if you think about it this way, then computationally, you basically said that I still have my intercept. Then I have my A effect when 1, B, C, little letter, okay? This negative against the positive, that's A effect. This is the positive effect. And then actually for AB effect, okay, the left wall, right wall crossing is confusing, right? You don't need to memorize how to generate that because computationally, negative A and negative B, negative 1 times negative 1 equal to what? AB is positive. Positive, negative, negative, positive is negative. Positive, positive is positive. Negative, negative is negative. So once you do that, since there are orthogonal contrast, so A contrast times B contrast become AB contrast, still the sum of the AB should equal to what? Contrast should equal to 0. You should only have 4 positive 1, 4 negative 1. Now let's introduce main effect C. And you can tell, okay, first time is, I'll usually said that this is, well, you guys don't know ballroom dancing, but this is 1, 2, 1, 2, and this is 1, 1, 2, 2. Jiluba cha-cha. I don't know if you know what that means, but basically there are Negative 1, positive 1, negative, negative, positive, positive, negative, negative, positive, positive. So C should be 4 negative, 4 positive. So anybody can stretch imagination. If I have a D, in order to have the main effect D should be what? 8 positive, 8 negative. So I need 16 trials in order to including D. What if I want to including E? 32. Okay, so usually people call this cube, right? And then they call anything beyond, it's called hypercube or hypercube. Okay, so here, so you can tell if I have the C effect again, A times C. Okay, negative negative become positive. Positive negative or negative positive become negative. Only when they are same sign. When AC are same sign means what? AC both low low to both high high. Those low low high high, they are positive. And if they are one low one high, they are not coordinated effort, then they are negative. So you can consider that what's positive, what's negative in two-way interactions. Coordinated effort versus contrast non-coordinated effort. Okay. Finally, BC the same way. And then how you figure out ABC? A times B times C. Again, if A times B times C, all three are negative, is negative. Okay. Anytime you have all three positive is positive. And every time if you have two positive, is still negative. But if you have two negative, one positive, you will have positive. So when you combine them together, you get this ABC effect. Okay? And now, finally, I can have this experiment. And this time I'm a little cheap because I only have, I have 8 combinations, so I only do 2 repetitions. And then you can figure out 8 repetitions, the average effect, the A effect, the B effect, the ABC effect, and then combine them into a sum of square and turn the sum of square into a ANOVA table. And let me find that for you. Where's module? Okay, let me find my module. 2 to the 3. Effect coding. Oh, I don't have that. Oh, right here. So I give you the PowerPoint, so you can do this. Oh, by the way, because in Excel, Excel doesn't just take the negative sign, so I use -1, +1. Okay. And then, of course, I'm lazy. I didn't do AB, then AB, A times B. I just directly can you see it now? A, B, C, sum equal to 0, sum equal to 0. And then, of course, usually, this is the way how I do it usually how I generate this, okay? I'll start by doing C, -1, copy, paste, +1, copy, paste. So now I have 8 of them, right? And then I just use the middle 4. That's right here. I'll use this, copy, and paste. Because that way will be 2 negative, 2 positive. And then, of course, copy one pair, negative, positive, paste here. Then I generate my ABC. Okay? I'm not going to give you anything just purely labor intensive in the exam doing this. That's wasting your time. The things I'm going to do is, you done your homework, you have your template. Now imagine you're in the real world. You're shaking hand, fake smile with some big shots, and the big shots say, here's our data, show us what to do. And you cannot say that, oh, let me do my positive one, negative one. You should pull out your toolbox and say, okay, let me start my analysis. Okay, now next, AB is A times B, AC is A times C, BC is B times C, and ABC is A times B, or products of ABC. No problem, right? And then when you're done, double check the sum of each one of them should be equal to 0, the multiplication equal to 0. Those two conditions, put that down, okay? The sum of the contrast equal to 0, the product equal to 0. That's called orthogonal contrast. If your sum is not equal to 0, or your sum of the products, ABC, is not equal to 0, they are not orthogonal, right? Why? This is from the vector analysis, right? Two vector are perpendicular is A dot B equal to 0, okay? Excuse me. So now, copy the observation. So I have the observation. And then you can take the average of all of them. Can you? That means if you take the average of all of them, it means what? That overall average is where your central station is going to be, right? 556. And after that, you do this. Okay? You assign the name of each one of the conditions. And how to assign that? If low, low, low is 1. If high, high, high is ABC. So first, there's two corners, no problem, right? Low, 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 high, high, high. Next, when A is high, the other two is low. Only A is high, is A. Only B is high, is B. Only C is high, is C. No problem, right? See that? Wiggle finger if you cannot see that. Okay. Finally, if AB high, only C is low, is AB. If AC high, only B is low, is AC. And only BC high, A is low, is BC. So we assign every observations, every conditions based on the A corner of this room. Agree? And then, of course, you can sum up the conditions of each one of them. You get that sum. Okay? Oh, by the way, I did not, copy paste from anywhere. Okay? I did it like what I asked you to do by hand. Okay? Finally, here is the tricks. How to figure out the A contrast. Still, using the observations, total times the contrast. So using this -1, +1 times this, you will have when A is negative, when A is positive. And then you will figure out your total A. Okay? So far, so good? See that? Same thing for B, for C, for A, B, C. So the contrast way to build this is that way. And then, of course, you need to square it, and then divide it by 8, divided by the number of replicas. So you get your sum of square that way. Okay? And repeat the same things. And now you have your sum of square built. And this time, when you build a sum of square, you will have your A effect sum of square, B effect sum of square, C effect sum of square, A, B, C, and everything's. Okay? And one things you can do, a lot of time I will do is this. I would like to make them smaller so I can just look at it and say that, okay, 5-digit, 6-digit, which one is big? It's obvious. Well, just by looking at this, which one is really big, main effect-wise? C, right? And then which one is small, yada yada. So, I do that. And the other things I'll do is, actually before I do the things, I will do a pie chart, insert a pie chart, and say that, show me which one is big, which one is small, that way, okay? Yeah, I'll keep it just for now. Okay, so that's the partition of the sum of square. And why this is important, okay? Later on, remember I said that sometimes we run an experiment with not enough money, not enough time. Then we start speculating, who can we sacrifice? Okay? You sacrifice the big guy, you sacrifice the small guy. You sacrifice the small guy for error term, okay? Sounds like politics, huh? And then, of course, once you've done that, you divide it by the error term, by their degrees of freedom. And this time, I'm kind of lazy. I'm just directly. Originally, it should be what? This divided by this divided by this, get your MS, and MS over MS, and for your degrees of freedom. But since, the numerator always divided by 1, so I'm kind of skip that, just say that, hey, denominator divided by 8. And you find the value, and then you use the F distribution, find the statistics when the p-value less than 0.05. And then you're done, okay? So now you basically create a sum of square, a ANOVA table, not using the central station approach. You're using the contrast approach. Next, okay? Let me see if I have it. No, I don't. Okay, so now let's build the sum of square using the dummy variable approach and using the effect and factorial dummy. Yeah, that should do it. Okay, so how to do that? You basically, we'll start with the positive 1, negative 1 approach. Here we go. So positive 1, negative 1 approach. Hey, we have A observation, true, right? But just like when we did a regression, I need to do this twice because I have 2 repetitions. So I have run 1, I have run 2. And if you have the run 1, you have the run 2, and you have your X transpose, and then you copy, paste, transpose, you get your X transpose X done. And if you have your X transpose X done, then you can use your X transpose X times X transpose X, you got your 8 by 8, right? Effect done. And then inverse transpose, and you have everything's done. And remember, when you have the parameter, since if you're using -1 to +1, it's 2 steps, right? So everything's need to be double. Because if I only use one, I'm only moved from -1 to 0. So I need 2 steps multiplied by 2. That will give you the effect. And then once you have the effect, okay, you can also run this multiplication conditions times the parameter. Intercept basically times A term, B term, C term, AB interaction term, you get your prediction. And then you will have your error term done. And once you have your error term done, okay, and the differences, okay, that will give you your sum of square error. Okay? And for your A term and B term sum of square, okay, you can calculate it 1 by 1. So when A effect is 37, right? Positive, negative, positive, negative. I have a bunch of A positive, A negative. I'm on that side of the negative 37, or I'm on this side of the positive 37. So a bunch of negative wall, a bunch of positive wall. And then what's the total variation? Depends on how many negative wall, how many positive wall. And when you combine them together, you get your sum of square. Okay? So your sum of square for A, sum of square for B, same thing. Sum of square B is what? The wall behind me against the wall in front of me. A bunch of positive, a bunch of negative. C wall is the ceiling against the floor. And then AB, AC, and then you get your sum of square done. Exactly the same things. Okay? You probably know, today of the exam or the homework will be come up with another one like this for you to play with, right? And for me, I use 2 repetitions. For your homework, I'll probably do 3 repetitions and so on. Okay, next. What if I'm using a dummy variable approach? The nice things about dummy variables approach is you don't need to double it, right? Because there's a bunch of -1 and +1. Okay? And so X transpose X. Okay? And here is the part that I think you need to be careful is this, okay? The sum for the contrast. You need to wash your face, huh? I can tell you're sleepy.
Yeah, just a little bit, sorry.
Yeah, that's okay. Hang on, another 25 minutes. Yeah. Okay, so for the contrast, or for the +1, -1, the sum usually equal to 0. Okay, but for the 0, 1 dummy variable approach, okay, it's usually equal to the number of contrast times 2. So how many 1 do you have for positive side? 4, right? So you have totally 8 points. Another 8 points, another 8 points. And then you're still using the combinations, but the tricks here is that when you finish your experiment, finish your regression, X transpose X, X transpose Y, when you're done, just like what we did last week, for the dummy variable approach, the parameter itself is the effect. Okay? Because you already moved from 0 to 1. Okay? So the parameter is the effect, is exactly the effect. And then if you want to figure out what's the parameter in the contrast way, you actually need to divide it by 2. Okay? I did have 1 year for fun in one of the exam problems saying that, hey, here are the output from one regression. Can you tell me what's the effect in the parameter of the other one? And really all I'm testing you is to realize that when you have -1 to +1 are 2 steps. And when you move from 0 to 1 is 1 step. Okay? But if you do that, everything can be done. But like I told you before, we're going to use contrast approach, okay? Because here, even a computation is a lot busier than needed. For Excel, these days is not a big issue. I can tell you that when I was, 30, 40 years ago learning this, we only have mainframe Fortran. We don't use with punch card. We don't do this. We did most of them by hand. And do a A by A inverse is no fun. Okay? Next. You guys ever seen punch card? Huh? Oh, okay. Okay, now let's do a now 4-way. Okay, and 4-way. I think I didn't bother to do the PDF, so I'm just do it directly. Uh-oh, too much. Okay, maybe let me do it this way. Can you see the? Oh shoot! Come on. See this one? Oh, okay, good. Okay, so I have 8 observation, right? I have 16 observation in order to satisfy 8 effect, right? So main effect. Here is my main effect. Okay, and usually when I do the main effect, I like to start from the D. So I'll have A positive, A negative. Good? And then copy the 4, 4 and generate 4 positive, 4 negative, 4 positive, 4 negative. Okay? And after that, 2 positive, 2 negative, and then of course the last one is negative, positive, negative, positive. And so once I have all this done, okay, you can actually name them without looking at this. All negative is baseline. All positive is A, B, C, D, engage. And then of course, if only A, B, C engaged, D is negative, A, B, C, right? And then you can have A, B, C, A, B, D. People tell me, for 2 by 2, 2 to the 4, how many 3-way effect? 3-way interaction, how many of them? Huh?
If this is 16, that would be 32, right?
Okay, then let's do it one by one. We have a baseline 0, 0, 0, right, or 1. We have a 4-way interactions, A times B times C times D, right? Here. Let me move over here. This is what I'm really trying to say. For 4 effect, I'll have 1 4-way interaction. Agree? How many 3-way interaction? 4. Why 4? Because 4-way means 3-way interaction means what? One of the effects missing. So D is missing, C is missing, B is missing, A is missing. So that will be my how many 3-way effect, 3-way interaction? 4 of them. Okay, so how many 2-way interactions? For 4 factor. C4 takes 2. 4 factorial divided by 2 factorial, 2 factorial become 4 times 3 divided by 2 is what? 12 divided by 2, 6. So how many two-way interactions? 6 two-way interactions. And how to figure that out? A can, okay, so now let's play dating game, right? A can date who? B, C, D. A, B, A, C, A, D. B can date, because you already count A, so you only count, B can date C and D. And then C can only date D. So AB, AC, AD. BC, BD, CD, 6. Okay? So totally, okay, for 4 factor, 4 main effect, okay, 6 two-way interactions, 4 two-way interactions, 1 four-way interactions. Everybody can see that, right? Yeah. So now the thing is that how to build that. We said that I'm using A is positive, B is positive, C is positive, small ab, small ac, ad. So I have 16 observation here. And then for A effect is AB interactions A times B, AC effect is A times C, AD effects A times D, BC, BD, AC, everything. Okay? And finally, A times B times C, AC, and now I have everybody. And here is my observation. Okay? And once I have my observation, and this time I'm even lazier. How many repetition I have? None. I'm only using 1. So if I'm only using 1, here is my A effect. A effect is what? The negative 1, positive 1 of A is here. Let me do this. Where's my split? View, split. Okay. So, okay, A effect is using A times the observation. B effect is using the contrast B times the observation. C effect, D effect, AB is using AB contrast times the observation. Senorita, we're good? Can you see everything? Good. So AB, AC, AD, and then ABC is using L2. Okay? Using this times ABC, ACD. Okay? Oh, we don't have this in your coming exam because I promised we only use the material before. But just can you see that, in the real world or in your future exam, not this coming exam, if you try to build a table like this in the exam, you're crazy, right? Yeah. So you need to kind of get your template ready. Okay. Those students who did really well in the previous year, especially one student, he's from Saudi Arabia, undergrad student. Okay, I gave him A+, and really nice recommendation. You know how he did it? He just tried to speculate how many different possible toolbox he needs. So he just built all the template, put them in different folder. So when I give them the exam, he immediately said, "Oh, I can use this one. I can use this one." Pull it out, plug and play, plug and play. Even the documentation, he, kind of canned the documentation ready. So he got everything's done really quick. And I said, "Why you do this?" He said, "Well, he got family business waiting for him. He can see how to use this at home." Okay? And So, just let you know that prepare your toolbox. Okay. If someone tell me that I don't like Excel, this is too dumb, I would like to use MATLAB or R, fine with me. Just show me your toolbox. Okay? And don't memorize it, okay? And then, of course, the same old tricks. Sum them up, and then divide it by 8. How come this time there's not 8 times 3, 8 times 2? Just divide it by 8. Because I only have what? 16 observations to build a contrast. Okay, so, and then of course, you square them, you're done. And finally, you will have your effect, and you will have your sum of square. Okay, here is something very, very important. Okay, this is probably the first really intellectual argument I would like you to have for this class. Okay, once I have my sum of square built, okay, the things what I would do is immediately, okay, copy all of them, and well, I can do it one more time. Okay, this is easy, right? You just do the same things, and once you do that, I will. Where is the? Here we go. I will go to. Oh, I have one here. I would just go to any one of them. Okay. Well, I already have one done. Let me redo it. So, paste special. Oh, I lost it. Okay. First of all, 16 observation. Every observation got a meaning, right? So, in other words, is that people just look at here. I have A many fact, B many fact, A, B, C, T interactions, every terms. Okay? If you count, how many terms do I have for my sum of square? Right? Oh, I can do this. Okay? I have 15 terms, right? Why? 4 main effect, 6 two-way interaction, 4 three-way interaction, 1 four-way interaction. I have 15 terms. Okay? How many observations do I have totally? 16. Minus where's the central station. So totally how many degrees I have freedom I have? 15. So 15 terms for 15 degrees of freedom. What's wrong with this whole picture?
Not many degrees of freedom.
You don't have any leftover for your error term. One way out is what? Hey, boss, I need more money, I need more time, so I can do some repetitions in order to investigate. But your boss could say what? You cannot do it. Give me your resignation. I'll find somebody who can do it, right? So now the challenge is that, okay, I don't have the error term, but I need the error. I don't have the error sum of square. I need the error sum of square. How to do that? Here's the way to do it. Okay, you copy this, and then you paste special value. Okay, you copy paste all of them, and then you just do a sort, data sort. Okay, And then you just say that, let me store the sum of square. Oh, I want to sort from big to small because I want to be greedy. Sort big to small. Okay, from big to small, you basically have this many effects. For sure, some of the terms here, it's so small, I probably don't want to investigate, right? Here are some terms I want to investigate. So you know that who will be investigated? A effect should be investigated, agree? AC interaction should be investigated, agree? So all the way down here. So sooner or later, you know what will be the argument people are going to have? Is that, remember what I said before? If here is a bar chart, okay, insert bar, okay, what will be the argument? I'll say that, hey, we're going to pass some student and flunk some students in this class, okay? Okay, if you say I only pass 4 students, I only get 4 students A. Number 5 will say that, what about me? Why cut me out? And then if you say, okay, number 5, you're in, I'll let you get A. But number 6, you get B, or you will be flunked. Number 6 will argue the same thing. What about me? Right? So sooner or later, you get into the question of where is the cutoff? Right? This is a fundamental system engineering problem, right? I need to make decision. I need to make highlight. I need to decide what, go or no go, who stay, right? So where to make the cut? One way you can do this is people will say that, well, you can tell there's an elbow point. And then you cut at the elbow point. The problem is the elbow point included or elbow point excluded? First of all, where's the elbow? Number 6 or number 5? One way to figure that out, of course, you can draw a percentage, okay? And then the percentage is going to show you exactly the same things. But what's the beauty about percentage is this, okay? Let me do it. So this is the sum of square of total. All the sum of square included. And then everybody divided by the sum of square total. Okay? And then you take the percentage. And if you take the percentage, okay, what you do is this. You do a finite differences. Upstairs minus downstairs. And what's the difference? Is, hey, from here to here is 9.7 jump. Okay? And then from here to here is 3.6% jump, 4.4, 8.1, 5.6. Can you guys see that this level of jump, okay, is in one scale? Here is another scale. People agree? So sometimes if the elbow point is not clear, I will do a finite differences using the jump. And the other things, okay, I can do is the following, okay? People look at here, okay? This is the very, very crucial points, okay, to talk about. A effect is the most significant main effect, agree? So if A effect is significant, AC effect is significant, AD effect is significant, means what? Could be, hey, A is the good big brother, A bring the C in, A bring the D in, so C work well with A, C work well with D, right? Right? A is Michael Jordan. Pippen's coming in, Pippen played really well. And of course, people will say, well, you play really well because you play with Michael Jordan. So Pippen's problem will be what? I need to show that I can do well without Jordan, right? Now, but you look at here, C effect and D effect, when they play by themselves, they're good. But they're not as good as their two-way interactions. So what does that tell you? The A influence is really, really strong, right? Because C by itself, D by itself, is not even as good as C play with D, C play with A, C play with... You guys, can you guys see here? The two-way interaction performed better than the main effect. What does that tell you? How many of you ever taste tofu? You know what I'm talking about? You like tofu? Boring, right? Yeah. It's sometimes worse than yogurt, right? But tofu is what kind of ingredient? If you do it right, it goes well with everything. But tofu by itself, not so good. Okay, so here C and D are tofu. Okay, they don't do well by themselves alone, but they do well with A. So AC, BC is good. Now here comes the troublesome part, the ABD part. I don't like this one. You guys know why? A effect, main effect is good. D effect is good. After I talk about A and D, suddenly I need to talk about this three-way interaction, ABD term. Have you ever seen B before we talk about ABD? Yeah, this is kind of like those science fiction, right? Star Trek, you talk about, here's a main alien character, here's another major alien character, Star Wars. Everything you talk about this and that, at least you introduce them first. What about this one? Why is this a terrible, terrible thing to have? You never introduce the B term, and suddenly you talk about ABD interactions. And people will say that, okay, nice picture, but where's that B coming from? You never talk about B. So if you ask me, should I keep the ABD term? I probably will say that very reluctant. Okay, unless I have some domain knowledge to cover that. But so based on this principle, okay, what is the game rule here? Always talk about main effect first. If you don't have the main effect introduced, try not to introduce the interaction term. That's the first things. Okay? Logically, how are you going to explain to your boss, hey, I have this ABD wonderful interaction. And your boss will ask you that, then what the heck is this things, right? What's this ABC, ABD? Right? He knows A, he knows D, but he never heard ABD. So whenever you try to introduce high interaction term, very, very conservative. One more, okay? Two-way interactions, I can draw a plot, parallel, good or not good. I know how to do that quickly. How many of you know how to explain three-way, four-way interactions? Very hard, right? Some of those classic novel, always hard to read. Why? Because they introduce too many characters. And you get confused. So the thing is that whenever possible, stay with the low-level terms. Okay? So there's a way we're going to introduce later. It's called resolutions. You got
15 minutes.
Okay. The game rule here is use the elbow points, use the jump, and then use your logics. The logic is that stay away from high interaction term. Unless you You know how to explain it or how you're going to do something about it. Okay? And that's also, I'm actually going to sit in a PhD student dissertation very soon. And he gave me some of his, report to read. And he said, oh, this is p-value less than 0.05, that p-value less than 0.5, this is significant, that's significant. And I said, so can you do anything about it? If you can't, why tell me this is significant? Right? You're an engineer, you should tell me, so what, who cares? What can I do anything about it? If you cannot do anything about it, no good. Okay? So if you do that, okay, there's a way to redraw this is the following. You see here, I basically copy the effect. But this time, when I copy the effect, okay, I have their percentage. So I start from the lowest percentage. So I start from 0, and every time I add one term in, I increase the percentage until 100%, right? And now, all I care about is draw the smiley face chart. Okay, I call it smiley face because the smiley face basically said that which effect is positive, which effect is negative. And then there will be a bunch of stuff bundled at the very, very bottom of that smiley face. Those are those terms that I can bundle together and sacrifice and said that, hey, since I don't have any sum of square for my error term, I'm going to use all the sum of square here. So here, basically the red one, according to this, okay, A effect stay, okay, and AC effect stay. Every one of them stay or not stay is the red one, and then our lump, or they call it statistics called pull all the sum of square together and use those sum of square and says that I'm going to call them error term. Okay? Oh, by the way, this type of polling approach, Takuchi, okay? You guys, if you take quality control from Dr. G or Dr. Sorali, they probably talk about Takuchi. And Takuchi calls sum of square polling. There are two different ways to pull. One is pulling things that I don't need to the error term. This is called pulling down. Why pulling down? Because you have the f-test in mind. Pulling down to the denominator. And sometimes you say, oh, I have too many terms. I would like to investigate one more. And said that, oh, I would like to have some of the error term investigated. It's called pulling up. Okay? And how important is this? Depends on who you interview with. If you interview with some of those TQM, car manufacturer, they probably Takuchi fan. They like to ask you Takuchi terms. Okay? But pulling up, pulling down is all based on that f-test. Where is the numerator and denominator? So every time if you do that, you will generate a smiley face. Okay? Okay. So once you generate a smiley face, you can rewrite your sum of square and build your ANOVA table. Okay? That way, your ANOVA table, you don't have error term. Where the error term coming from? From those things I don't want, I don't need. Okay? Okay, people, this opinion, you like repetitions experiment or you like this polling approach of experiment? Well, let me ask you this. In industry, which approach you think industry like? polling, because polling is basically said that investigate what I can investigate, things I cannot investigate, I use for something. Okay, and I joke about it before. How many of you ever buy the rotisserie chicken from Walmart or Food Lion? Okay, I see this single mom with kids shopping, right? The legs, the chicken breast for salad, okay, and then they still have the ribs and some of the stuff. They will use that for chicken stock. So entire rotisserie chicken, every piece get used, nothing wasted. Okay, and when I look at that, I said, pulling up experiment, well, pulling down experiment. Okay, I'm not joking. I'm serious. What's wrong with the single mom economics? It's how we survive here. Okay. So next. So we can do the pulling up, pulling down, and then we still can do our regression approach. I still can have my dummy variable. I still can have my contrast approach. So when I have my contrast approach, you copy down everything. Let me make it smaller. Hey. Okay, so this part, exactly the same thing as what we had before, right? And then you will have your intercept term, you build your x transpose x, you build your x transpose x inverse, x transpose y, you get all your parameters out. And since this is the -1, +1, oh, by the way, I can even, just by looking, when I grade something, I can just look at the main diagonal and say that, oh, this must be the -1, +1, because it's only main diagonal. And then you will have your effect, your parameter, and you use your parameter, you build your predictions, okay? And once you build your predictions, you're pretty much done here. You cannot do much since this is a pulling up, pulling down experiment. There's no error term. There's nothing left we can play with, okay? And the only reason I'm doing it is later, this is a stepping stone for something more fun to deal with. Okay, let's do the dummy. The dummy is the same way. Okay, you build your 16, x transpose x, x transpose y, you have your total sum of square. And the only things you can double check here is your total sum of square is, no matter what, is the total sum of square. But you can have your total sum of square without using this complex approach. Why? Because what do you call that things? You just calculate the variance of the whole thing times 15. Okay, we're done. Okay. Before I close today, oh yeah, you can have your regression, intercept, your effect. They're called a regression approach. The only things I would like to challenge you or to ask you to think about is now I'm showing you having repetition, without repetition, industry like this, don't like that. Okay. What else do you think that should be in the experimental design according to this line of thought. How many observations I need for this 2 by 2 by 2 by 2? 16, right? Is it possible somebody say, oh, I would like to investigate E, investigate F, and adding more stuff. And then in Dr. Chao-Zu Lim's language, you get into the MP complete, right? More and more to search. And what are you going to do? Now you basically say that even I'm using 1 repetitions, I'm going to be 2 by 2 by 2 by 2 by 2, 32, 64, 128. Sooner or later, I still need tons of observation. Okay? So the next things we're going to do later, it will be even tear this house apart. We only investigate half of the house. And using only half of the house, or even 1/4 of the house, to figure out what we need to figure out. So now I'm not only using 1 observation and pull stuff together as my error term. Even that I consider is not stingy enough. I would like to, cut it down even smaller, right? And then investigate for other stuff. That is what we gotta get into called fractional factorial design. Okay, let you go unless you have any questions.